Then I would like to introduce one of the examples relevant to the excited state, which is solvent effect. This represents the absorption shift due to the solvent. The absorption shift meaning the shift of energy levels. And as you've already understood, the absorption, light absorption, is the phenomenon where the ground state and the excited states are involved. Here's one of the example called the solvent chromism. You can see many different colors of the solutions, but actually the color is coming from the same molecules. The only difference is a solvent. The solutions are colored by one same molecule, but the color has many variations because the energy levels of the dye, the molecules, are changed depending on the properties of solvent. So here's why. You can see that now while we are observing the light absorption here from the ground state to excited state in some of the solvent. But when this molecules is solved in a different solvent, the energy level is changed because of the condition of the molecules. For example, if your molecule are polar or non-polar, then the energy or stabilization of molecules changed by the configuration of the polarization. For example, if you have a carbonyl which has a positive and a negative charge in the molecule, and then water can change the orientation toward the molecular side depending on the charge of the molecules. And for example, if the molecules are in solvent A and then move to solvent B, and this gap is the energy of the light absorption, and this one is bigger case, which is called blue shift. Because this energy is larger, meaning the corresponding wavelengths move toward the shorter wavelengths. And shorter wavelengths means blue side. So that's why it is called a blue shift. On the other hand, if the shift is from this one to this side, so energy becomes smaller. In this case, the wavelengths moves toward the longer wavelengths, which is called lead shift. That's a mistake. And I would just remind you that sometimes people make a mistake that only the excited state is stabilized or destabilized, but this is not true. So you have to think that this difference. So meaning that not only the excited state, but also ground state also shifted. And how much stabilized for each of the state, like ground state or excited state, is important. For example, in the case of blue shift, stabilization solvent must be larger in the ground state than compared with excited state. That's why this gap becomes larger. On the other hand, in a red shift, the stabilization by the solvent is smaller in the ground state and compared with excited state. That's why it could happen. Right. So it's already kind of mentioned, but in the case of n-pi star state of carbonyl, and the n-pi star state, it's in the ground state, electrons are more because this one, two of the electrons are occupied in the non-bonding orbital, so electrons are quite biased toward the oxygen side. So meaning that CO, carbonyl, as in the ground state, positively and negatively charged. So this ground state is more stabilized in a polar solvent, this case. So in a polar solvent, the ground state is more stabilized. On the other hand, in an excited state, these electrons are coming to the pi star state. So meaning that the electrons are not biased toward the oxygen side. So meaning that not much stabilized in a polar solvent. That's why the stabilization this side is smaller. So in the case of n-pi, when we think about the n-pi star state of the n-pi star related light absorption, the blue shift could happen in the polar solvent in the n-pi star state.